So thank you very much, everyone, for joining this workshop. I don't know if you are seeing the slides. This workshop is about a microservice-based autonomic traffic control in 5G and beyond. Today we have a very nice list of speakers that we are coming from the Terraflow project. I guess that you are able to see the slides. I don't know if you're seeing them. Okay, right now. So in the next slide, we see the list of speakers for today. We try to give an overview of what is about this microservice-based autonomous traffic control in 5G and beyond, that Terraflow objective. That is one of the ITP phase 3 projects. First, I will start myself by introducing the need for a cloud-native SDN controller. Then Juan Pedro Fernández Palacios from Telefónica will talk about the Terraflow architecture and the different use cases. Then we have Hans-Tim Habibi from Telenor talking about transport SDN controller and business models. Later on, José Miguel Pulito from Volta Networks will focus on transport network slicing on IP over DWDM networks. Then we focus on one type of transport network. That's the SDN control of wireless transport networks in 5G and beyond. We enter between be given by Michele Milano from CIA. And then we will orient and present how we could apply this little lecture on smart contracts to transport networks. That is talk that will be given by Rafael Bova from NEC. And finally, Daniel King is able to present the latest trends on transport SDN standardization efforts. He's from consulting, has a lot of experience in SDO, so we will benefit of this great overview. In the next slide, you can see the title from my talk, and which I will try to motivate this need for this transport SDN controller, which needs to be cloud-based. So what we have seen in the last 10 years is that SDN has been in the market with great success, but we have not seen still great adoption by the operators. The cloud is evolving quite slow pace. There is not a clear path of SDN introduction in the operators. There's a big need for automation. That's something that will benefit the deployment of SDN in the operator's network. So when we think automation in the field that will benefit this SDN adoption, for beyond 5G networks, we have massive SDN flows that will be needed. Low aggregation at the network core is not efficient and does not provide specific services. So the intention is that we provide more dynamicity to the transport network. That's one of the objectives from our controller. And also we want to bridge the gap between the network and the computing paradigms. So we need to address all the resources in a unified way. So compute and network have the same. There is no the need to break this BIM or wheel paradigm. So we need to do networking and computing in the same way. Finally, we need also to introduce security as we are automating, not to secure the networks, so the networks are able to autonomously resist attacks. So for the next slide, we will observe the different key points that need to be tackled if we want the latest state-of-the-art SDN controller, which is able to fulfill this need of automation that needs to be brought inside the operator's networks. So we need to have our SDN controller based on microservice architecture, and we need to have use case-driven use cases For IP and optical networks, we need to have a smart connectivity with integrated edge computing and storage resources. What we also want from and we demand for the SDN controller is the dynamic adaptation of the services based on different flows and application requirements. Then we need to have novel kinds of interaction between humans and digital systems, and our SDN controller needs to provide services for this. We need to complement the lack of commercial products for SDN. We are proposing an SDN controller with an open source license, like Apache, and we also want to contribute to other open source software. So if we want to go to the next slide, we will see the main contributions for Terraflow. They will consist on network usage integration and optimized management of network resources. It will introduce the concept of transport network slices by adding the smart traffic interconnection and the scenario assurance. We will also foster security and resilience with, using artificial intelligence and machine learning mechanisms. We also propose the usage of distributed ledger and smart contracts. And finally, we will provide flexible connect compute technologies and architecture. So these are the main contributions for Terraflow that we want to stress. And if we check in the next slide, you will see how SDN controllers look like today. So today we can observe the status of these state-of-the-art SDN controllers. They are basically mostly monolithic. So if we check for ONOS or Open Daylight, for example, they are based on microservice-based architectures. Only we have micro ONOS that are starting to follow this process of disaggregation, but it is not fully disaggregated yet. We have also the distributed SDN controllers up to date. They might not meet this excessive traffic demand for beyond 5G networks. So we need to also be able to handle a huge number of flows. We need to reach the SDN deployments across multiple transport networks and with multiple access technologies. So this is still open challenge. Still, we are in our project, we are addressing optical and wireless links. We are also addressing IP routers. So all these technologies need to be integrated in a holistic platform, and that's something that we have still not seen in today's SDN controllers. Also, there is still a vague connection between the concept of a slice and the SNAs that the slice is providing, and we have only seen today in SDN semi-automated deployment. So that's what we have right now, and the state of the art. And in the other side, in Terraflow, what it wants to propose. So if we see what Terraflow is proposing, you can observe that Terraflow tries to bridge a gap between the state of the art and the different topics that we were requesting from an SDN controller, such as a disaggregated cloud-native network operating system based on microservices. It also introduces this distributed control plane, which is able to achieve at least an order of magnitude higher flow processing performance. We also are providing this transport level network slicing for reaching differential distributed SDN deployments with multiple access technologies. We have slicing coupled with complementary network operator SLAs. And finally, we want to provide these fully automated zero-touch deployments. So these are the different topics that we want to address with Terraflow. And right now, I will just leave the floor to Juan Pedro Fernández Palacios from Telefónica in order to present the Terraflow architectures and use cases.
Thanks a lot, Ricard. Yes, I'm pleased to present all of you the Terraflow architecture and the use case methodology we are following in the project in order to design this Terraflow SDN architecture. Please, can we go to the next slide? Thank you. Here, okay, we can say is that in Terraflow, the application or the SDN is targeting the transport. That is the backhaul, the core network, covering IP, optical, microwave. And in this network segment, what we are looking for a standard SDN architecture, because I think, as Ricardo was mentioning during the first slides, okay, we started to talk about SDN many years ago, but currently we don't have a wide adoption of this in the industry, in the operators, like for example, in my case, in Telefonica. And one of the main reasons is the lack of a standard solution enabling multi-vendor interoperability. We have vertical solutions enabling automation in SDN, in this case, for example, for the transport network, but are mono-vendor ones, where a single provider is offering from the network application or the automation tool, the SDN controller, and also the network equipment. However, the reality or the day by day in the operators is different. We have different vendors in the different layers, in IP, in optical, in microwave. We want to have vendor agnostic SDN controllers, also in order to with standard interfaces, so that we can implement on top of these SDN controllers any new application in order to enable the network automation, in order to enable, for example, automated service provisioning, planning, or, for example, artificial intelligence-based cybersecurity or optimization tools. According to that, in Terraflow, we are looking for this. We are defining these standard and open interfaces from the SDN controller towards the applications, in order to enable this an agile introduction of these network applications in a network that could be multi-vendor, as the real networks we have in the operators. Please, can we go to the next slide? Thank you. Here we can define two different. We can classify the interfaces that are needed in order to have a multi-vendor and a standard transport SDN architecture. We can classify them into two types. On the one hand, we have the northbound interfaces from the SDN controller to the network applications. These are we name the northbound interfaces. These northbound interfaces should provide abstracted information from the network toward the network applications in order to hide any, let's say, vendor proprietary information. So they have to, the key for the northbound interfaces or the program, these northbound interfaces enabling the network programmability is that they should be common for any operator. They could be, of course, for any operator and for any vendor provider, and could be applicable for multi-vendor networks covering network elements from different network, different providers in the IP, the optical, the microwave, the end-to-end transport network. So we have the two kinds of interfaces. As on the one hand, the northbound interface from the SDN controller towards the network application. We need these open and standard interfaces in order to open the market for the network application, so that any software developer, any company could directly do network programming over multi-vendor networks using always the same interface and avoiding ad hoc implementations per vendor. That is what is happening nowadays. And on the other hand, we also need standard interfaces, the southbound interface from the SDN controller toward the network elements, in order to have a vendor agnostic device configuration. This is key in order to expose or to enable this network programmability with different vendors, with different technologies, and, for example, opening the door to new technologies like the disaggregation or disaggregation boxes. This is one of the topics addressed in Terraflow, where we can have software and hardware from different providers. According to that, we have also to evolve from the current proprietary configuration interfaces based on CLI and specific and proprietary templates per vendor and equipment towards a vendor agnostic device configuration model based on data models, standard data models. For example, in particular, we are focusing on OpenConfig for the IP and the open terminals in the optical network, and ONF models for the microwave. Okay, this is quite ambitious, having standard interfaces for device configuration and also to enable network programmability. This and what is something key, we think, is the methodology, how to achieve that. We have to go step by step, use case by use case. Because one of the problems in the past was trying to have a single solution covering everything since the beginning, all the potential, every parameter we may need to configure in the network. If we want to have 100% ready solution, probably we will never have it. So the key is having something working step by step and use case by use case in order to have a gradual design, implementation, and activation process. And this is what we are doing in Terraflow. We are working in a use case methodology. Please, can we go to the next slide? Please, next slide. Okay, thank you. The use cases, according to this use case methodology, we are defining a set of use cases covering everything we may need in a automated for network automation in currently in the midterm and even in the long term, where the traffic dynamicity and the number of flows in the network will be much higher than nowadays. These use cases are covering, for example, inventory, topology, service provisioning, for example, network slicing, that is key already for 5G and also in the future, for example, in order to enable network sharing among different operators, monitoring, performance monitoring and telemetry, use cases on that are also key, automation in any case, service provisioning, or for example, the fault management. We also have use cases about policies, routing policies, or networking policies to be implemented in the network, machine learning, blockchain, interdomain issues between different operators and different vendors. So it is, okay, we are splitting the problem among different use cases and defining a specific solution for the interfaces. What are the requirements in terms of, for example, the parameters that should be configured in the southbound interface, and also the service modeling that should be exposed also in the northbound interface toward the applications. And finally, also in Terraflow, we are working on the applications that could directly interact with the network in order to provide these use cases. Please, can we go to the next slide? In order to do all this work that is starting from network design, we define the use cases, the requirements. Then we design the interfaces, the southbound, the northbound interfaces. And finally, we also implement the applications in order to build up the complete use case in a multi-vendor, very important in a multi-vendor and standard transport network. Okay, in order to do all this process, and the final one is the implementation and the activation in the operator network. In order to do all of this, we need an intensive testing work. According to that, in Terraflow, we have different testbeds. One of them is the one that is represented here, that is the Telefonica Future Network Lab. In this lab, we are implementing the complete SDN architecture for the transport, and going into the details. That is, our target is having a vendor agnostic SDN controller implementing the northbound interfaces towards the applications that will directly interact with the multi-vendor network. The service northbound interfaces are typically, in our case, based on, of course, should be standard ones. And we are targeting the service modeling in the ITF, and also the service models in the ONF, in particular the transport API, because for the optical domain, the northbound interface that we are considering is the transport is the TAPI, the ONF TAPI. In the optical domain, we foresee a single or a given SDN controller per vendor, because there are lots of proprietary issues in the open line system that, okay, we think will keep proprietary will for a while. We are looking for disaggregation or interoperability in the data plane for the open terminals in order to have a partial disaggregation with line systems from one vendor and terminals from a different one. In this case, the southbound interface is the open config in order to configure the transponders, but the northbound interface is TAPI. And we are focusing all the work on identifying the gaps in order to cover the use cases on TAPI. Second, for the IP, we're working on the ITF models for the northbound interface and netconfig and open-config modeling for the IP routers in order to build up the different use cases. In the microwave, we are working on the ONF 532 modeling. All these models are in the lab, are supported in the network devices and also in the Terraflow operating system, the SDN controller, in order to test end-to-end how the applications could interact with the network through the northbound interfaces and the SDN controller in order to configure the different vendor domains and the different technologies, also with the standard southbound interfaces. Please, can we go to the next slide? In this slide, we can see the interdomain scenario, because the Telefonica Future Network Lab is focused on transport, the different transport domains, the microwave, the optical, and the IP. But we are in Terraflow, we are also extending the control also to the radio access with this interdomain scenario. In this case, this lab is running in CTTC on the Adrenaline platform and is combining SDN and NFV for packet optical network, and also important, the key in this project is the edge computing at the network edge in order to prevent or have a highly scalable solution for teraflows of connections in 5G and beyond, and it's also covering the access or the integration with the RAN, with the radio access network. Finally, if we go to the next slide, we have another testbed that is also hosted with Telefonica. That is the cybersecurity scenario. Security is key. We need two motivations or two main needs in Terraflow in order to work on security. On the one hand, we need to define and propose solutions in order to defend with the network from the external attacks. According to that, we are using the telemetry measures and we are defining some algorithms in order to identify what could be anomalous workflows, identify what could be, because important is that we cannot enter into the data user information. We don't have, everything is encrypted, so operators do not have access to this information, and we have to provide these security tools according to the information we have in the network. So using algorithms and so on. On the other hand, we also have to protect the interfaces in order to take the information from the network elements and also the northbound interfaces towards the applications, providing authentication, encryption, and so on. So in terms of cybersecurity, we are focused on these 2 points, protecting the interfaces and also introducing artificial intelligence, machine learning, algorithms, taking information from the telemetry measurements in order to identify potential attacks to the network and react against them. And okay, I think that's all from my side. Now I can give the floor to Hane, that will present also the commercial and the exploitation plan from Terraflow. Thank you.
Thank you, Juan. So I'll talk about transport as a controller and business models. I'm from Telenor, and I'll prepare this presentation with Esther from Atos. And next slide, please. So to talk about business models for SDN providers, SN must solve a problem for a telco operator. So that is one thing that I'll look into. And also the SN controller, it is not only by itself, it is many stakeholders that are dependent on each other in creating value with SN technologies and that are sharing revenues. So the SN controller is part of an ecosystem. That is something I'll come back to. And finally, the SN ecosystem will evolve over time with a high degree of uncertainty. So I'll come back to these three topics. But first, on the first slide, I will say something that is a preliminary analysis based on the proposal and some assumptions that we have made there. So next slide, please. So this as a Terraflow and the SDN controller is based on an assumption and on a trend that in future we have a huge volume of data and data flows and also lots of malicious attacks. We have also some assumptions on heterogeneity. In this high volume market, there will also be richer use experiences, heterogeneous distributed services, and high dynamicity. So it's going to be high volume, but very complex market. This is what we are looking at. And in this market, we already in our proposal suggested some stakeholders. And we said, we also pointed at some pains that already are there, mostly for MNOs, but there are pains such as you cannot prioritize use cases. You don't have an overview of compute network from edge to core. In future business ecosystem, to the right here, we understand that to administer high volume of complex contracts and transactions, that's a lot of insecurity, and they're expensive and it's slow. So there are lots and lots of things that needs to be solved. And to solve these pains is the core of a profitable provisioning of SDN controls in the future. So next slide, please. To start to look at this this business model of the SDN controller, we look at the very, very basic business relationships. The SDN providers providing something to the MNOs who provide something to the customers. And in our project, we are now validating the problem of the MNO. And we are using the business model canvas, which you perhaps know already for this, but before going into a business model, we need to understand the value proposition, and we use the value proposition canvas for this. And we go into the pains, the jobs to be done for the MNO, and we try to understand that and validate that through iterations with the partners, and also using many other sources to understand this. And next slide, please. And at this point of time in our project, based on the initial thoughts in the proposal, but also many other sources, this is where we stand. Regarding this future outlook of a high volume complex market, the MNO core of the MNO pains is a very inefficient way of working. And Juan pointed a lot of these things already, but these has some implications that it's really unfortunate for the MNOs, because when this very inefficient way of work leads to that you don't have a cost efficient operation in a high scale market. It's not energy efficient, but not the least. This is also an obstacle to create new and different business models that we really want to do as mobile operators, but also that the market demands. The market wants to also to extract new types of revenues from all those enterprise and different verticals, and they want to. And MNOs, they also have struggling with enable market innovation from all those other third parties, and the ecosystem has challenges with growing and evolving. So with many different, next slide, please. So with many different sources, but also working hard with this in Terraflow, we're looking at the value proposition. So this framework here is you can see as a summary of the things what we have found. But one specific, next slide, please. One specific pain pointed at is this lack of flexibility that we currently have in our operation, because we have to ad hoc adapt to vendors all the time on their interfaces, and it's extremely time consuming. It's lots of manual job to configure across vendors as we do today. And again, this is, of course, these are obstacles to address this future large-scale market. Next slide, please. So just to summarize, the technology pains are mainly connected to proprietary technologies and interfaces, but also we have identified that there is a cultural pain within the MNOs, and that is the MNOs are they do not dare actually to open the interfaces for customers' innovation. So there are more things to work with, which perhaps not the SDN transport controller will address. But the point with the business model is that the SDN transport controller technologies that we are developing in Terraflow, they must address these pain points in order to realize the potential profit that is in this market. Next slide, please. So, okay, we're talking about a very basic business relationship and the MNO pains. Next slide, please. But the reality is that this is an ecosystem with many stakeholders that together create value for the MNO in the first place, and then for the customers in the second place. And they are dependent on each other in value creation. And this is the core characteristic of an ecosystem type of market, the dependencies. You cannot do this alone. You have to mobilize all the other actors to create together with you. And all of these also then have to have their own business models and extract revenues from the market, each of them with different business models, different cost models and different revenue models. And this is what we are going to work further with in Terraflow, this complex ecosystem and how this complex ecosystem together address the MNO's pains and provide the solution. So next slide, please. And we already see that there are more stakeholders than we initially described. Of course, the vendors, which is not in this slide, but vendors, we have to understand their point of view. But the inter-MNO business relationship is, of course, very important, and cross-border business relationship, and not the least. All those application providers, third parties who develop the net apps for and together with enterprise customers in verticals for whatever purposes they need connectivity. So next slide, please. We also have to understand that when we're talking about the future market and an ecosystem in the future market, in a future high volume market, high data market with lots and lots of data, we are talking about a future where we want to be and we think that we can extract profit. But the fact is that we are in a very early phases of this. And before we get to this final market, there is an emergence of an ecosystem that we need to cater to. And we will study the emergence of this ecosystem, which is subject to huge uncertainties. Next slide, please. What we do know is that from ecosystem strategies is that to make it easy for stakeholders to take part in value creation with anything that has to be open technologies, API standards, that is really important, but also to make it attractive for stakeholders to join this ecosystem. I mean, everyone needs to profit in order to find it interesting to take part and to solve problems for them and us, and to create the STM ecosystem together. So next slide, please, just to summarize so shortly. And so what we are doing is that we are, with the business model, we are refining the telco operator problem to be solved and the value proposition. And then we are looking at the STM ecosystem, we map stakeholders, their dependencies, and their many different business models. And then we aim to put this into an ecosystem and look at the evolution, how the ecosystem may evolve over time. So thank you. That was what I wanted to say.
Thank you, Hans-Tim. Let's go to José Miguel Pulido from Volta Networks.
Thank you, Hanne. Thank you, Ricard. The goal of this talk is to explain what is network slicing in the context of 5G networks, what are the benefits for customers and operators, and what are we doing in Terraflow about it. Next slide, please. Thank you. So network slicing in the context of 5G is about sharing the same physical infrastructure between different entities, and each one getting a dedicated subset of the resources. There are actually two ways to achieve that in the context of 5G, and we call them soft and hard network slicing. Soft is about using BPM flows and quality of service in order to allocate different resources to different traffic classes. And hard is actually about creating virtual networks, multiple virtual networks on top of the same physical network. This can be accomplished because each of the components of the 5G network, namely the radio access part, the backhaul network, and the mobile core, have the ability to use virtualization and disaggregation in order to using software in order to have multiple components that can be virtualized, as we will see. Next slide. For the case of soft network slicing, each traffic class basically gets an QS class index, a QCI, and based on this QCI, each of the components of the 5G network will treat traffic in a different way, right? So the RAN part will actually do different. The scheduler in the RAN will treat different traffic in different way. The user plane function in the mobile core will also process, assign different resources to different types of traffic with different QCI. And in the context of the backhaul network that connects both components, we will use the quality of service primitives in IP networks and optical networks in order to apply quality of service functionality. Even more, the 5G 3GPP standard actually defines a set of standardized slices based on QCI. And for example, the number one applies to low latency applications. The number two applies to IoT applications. And number three applies to high bandwidth applications. Just to note that this specification about the standardized slice types, or SSTs, have been created for the RAN and the mobile core part, but not about the backhaul network. There is no specification for the backhaul network. So in that case, we actually need to rely on existing IP protocol standards. Next slide. What happens with soft network slicing is that applying quality of service over VPN flows may actually not be enough to provide end-to-end guarantees. And this is because the mobile operator can only has control over what happens in the cellular network. But if, for example, the other end of the communication is somewhere in a data center or in the internet, the delay between the mobile core and the data center is unbounded because there is no single entity that manages that, right? So the guarantees that soft network slicing can provide are somewhat limited, and therefore that definitely has an impact on how applications, low latency applications such as connected cars, for example, or IoT sensor or IoT traffic can be handled in this context. So as we will see, hard network slicing comes in order to provide a solution for that. So hard network slicing is the ability to actually create multiple instances of the same component. For example, in the case of the radio access network, we can have multiple virtual schedulers over the same RAN, and therefore each virtual schedule may actually be part of its own network. When we say, and that means that in addition to this virtual scheduler, the disaggregation part of hard network slicing is that you can actually break the radio access part into 3 separate entities: the radio unit, the distributed unit, and the centralized unit, and you can place these different units in different locations. So for example, you may have the RU and the U in the cell side, and you may find the CU in the edge side. And you can actually have multiple instances of these groups together, each one becoming a separate virtual network on top of the same radio infrastructure. Similarly, all the components that form a mobile core has been defined in an architecture that can be implemented through microservices, and different service mesh instances can be created, meaning that, for example, you may have one mobile core instance that runs on a regional data center, but you may also have another mobile core instance, or at least part of it, for example, the user plane function that runs on an edge side. And therefore, you may actually have one mobile core for regular applications, and you may have a separate mobile core running closer to the user at the edge for low latency applications. And in the same way, in the backhaul network that you connect both the radio and the mobile core, even though it has not been standardized for the 3GPP, you may need the similar functionality. In a sense, you may actually have one virtual network dedicated to low latency traffic with application backends terminating at the edge of the network, and you may have separate virtual networks to carry regular internet traffic. So I have hinted a bit on the benefits of what hard network slicing enables, but they are here. So the first one is that it enables edge computing, because it allows you to have multiple mobile core mesh instances, one running in the original data center, as it happens today in 4G, but also you can add additional instances running in different locations, and for the ones that will run in the edge node, in the edge of the network, in the edge data centers, that means you will be able to terminate GTP tunnels there, and therefore you can collocate the applications backend in there, which means that the end-to-end traffic will remain for the first time within the operator network, and therefore the operator will be able to provide end-to-end delay guarantees, and therefore be able to support low latency applications. It also, not yet, sorry. It also opens the door for new business models, because, for example, virtual networks that an operator can create, the operator can use them for internal use, for example, to assign them to different types of traffic, but the operator can also use them for external use. They can actually expose them as a network as a service for customers. So that enables, for example, the carrier over carrier use case, where the operator that owns infrastructure creates a virtual network, and that virtual network is handed to MNO, so MNO can actually manage the virtual network and provide services to their own customers. And the ability of having these separate virtual networks, it means that you can actually dedicate resources separated administratively between them for different types of applications. And finally, you can actually combine both, right? You can have a virtual network where you configure VPN flows on it. So what are we doing in Terraflow within this framework? So, for example, we're defining different customer services. We call VPN++ to what will be the equivalent to soft network slicing, where essentially it's a VPN flow with certain guarantees in terms of performance. On the other hand, we also would like to support the network as a service, where an operator exposes a virtual network as a service to other operators. The interesting differentiator here is that the customer is the one in this case that is managing the service, because it's the customer the one that will be managing the virtual network. And in order to support these two services, the operator has what we call a toolkit. So in a sense, in addition to the physical infrastructure of devices and links, it can also have virtual routers, which essentially is a way to do device slicing, as well as virtual links with technologies such as FlexE, for example, in order to slice physical links. The operator will also have different tunnels for soft network slicing, MPLS VPNs, GTP tunnels, etc. And in order to achieve disjoint paths, the operator also has available technologies such as the PCE plus segment routing in order to do traffic engineering. This is a visual representation of the network slicing within the context of Terraflow. If we start bottom up, we have the physical infrastructure formed by devices. On top of each physical device, we can actually configure multiple virtual routers, meaning that we achieve device slicing because each single physical device may host multiple virtual routers. And then what we can do is we can actually group multiple virtual routers across different devices within the same administrative domain using technologies such as RBAC, for example. And for each set of virtual routers and the same administrative domain, we call that as a virtual network. And that virtual network then can be used by the operator to use it internally for different types of traffic, or to expose them as a service to customers in the form of a network as a service, right? So as you can see that, for example, the operator may have a default virtual network, which will correspond to today's physical network on which VPN flows are configured directly. But the operator may also have another separate virtual network. For example, I call here edge, which is the one that will be carrying the traffic from the cell sites in order to the edge of the network for those latency-sensitive applications that need to benefit from edge computing. And in this case, the VPN services will be going from the cell sites and will be terminated in the edge of the network so that they can access the traffic can access the collocated application backends in the context of mobile edge computing, for example. And in addition, the operator can also choose to create these virtual networks on top and then expose it as a service, right? For example, it may give the control of this virtual network to another carrier to support the carrier over carrier use case, or to a virtual MNO that can also benefit from it. One thing that as a consequence of having a rich toolkit is that operators can actually implement these network slices with different levels of isolation. For example, for the VPN++ service, this VPN flow with certain performance guarantees, the operator may use tunnels over a physical network, may use tunnels over disjoint optical and IP paths, thanks to traffic engineering capabilities with using PC and segment routing. It may use tunnels over a virtual network, or it may even use tunnels over a virtual network with some disjoint paths. And similarly, in order to expose a network as a service, the operator may choose to do that over physical resources. It may actually dedicate different physical resources to different customers, or it may use a combination of virtual and physical resources, or it may use just pure virtual resources in order to create virtual network. So it will be up to the operator to decide which level of isolation is best suited for each type of customer or customer offering they decide. And of course, based on what we have been mentioning during the entire session, is that this cannot be done in isolation or in a proprietary fashion. Instead, it needs to be done in a standardized and open way so that it can support a multi-vendor scenario, right? So there are different efforts within the community in order to standardize both the services and the tools in the operator toolkit. And there are other efforts that they may actually start as part of Terraflow, given the novelty of the services that we're offering here, right? So, for example, for VPN++, the IETF is actively working on service models for both L2VPN and L3VPN, and as well as to realize those VPN tunnels. It's also working on the network model, on network models for L2VPN and L3VPN. When I mention network models or service models, I refer to the use of the Yang language in order to specify the requirements of these services. What we are seeing is that there is no such equivalent effort for network as a service or virtual networks, and we hope that we'll be able to advance in that direction. Finally, just to mention how all this fits into the Terraflow architecture that we have mentioned. If you see here the overall picture from the OSS system that configure services through the Terraflow SDN controller in both the IP domain and optical domain, you can see where the different service levels are being applied. And what we can see here is that the Terraflow SDN controller will actually need to have the notion of a network slice, right? Because if you are going to create virtual networks on top of the physical infrastructure, you are going to need to incorporate the notion of a network slice controller here. And if we go to the next slide, just as to mention, these are different possibilities within the Terraflow architecture on where the network slice controller will fit, right? It may be part of the SDTN, which is the part of the SDN, the Terraflow controller that deals with services before those services are implemented at the different layers of the network. So it may be the network slice controller may be part of the SDTN as shows in A, or it may be actually outside as a separate entity as shows in the option B. And given that it operates at the service level, it may interact with the different SDN controllers for the different domains separately. Alternatively, the option C and D can actually also capture when you implement a network slice controller for each of the domains. Up to this point, this is an open question for us in terms of architecture where the network slice controller will fit in, and we hope that this is something that we'll solve as part of the, or we'll have proposal as part of the project. And thank you for the for attendance.
Thank you, Miguel. Now we will present one specific use case for wireless transport that we will introduce by the CI before.
Yes, hello everybody. Michele Milano speaking. Okay, now we will focus on the advantages of the SDN in managing a microwave network basing on our experience as a as a company that has experience in the microwave network. So managing a microwave networks presents several technological challenges. First of all, you have to face with multiple frequency bands, microwave, millimeter wave, terahertz. And so there is the need for a trade-off among bandwidth, reachability, and reliability requirement. You have a time-varying, unpredictable radio channel due to precipitation or multipath fading, interference, and so on. The link capacity dynamically can change depending on channel conditions. So, for example, using adaptive modulation functionality. Then you have to manage with multiple link aggregation at physical layer. And as regards reliability, in general, in a microwave network, there are few redundant paths because most topologies are chain and tree, only sometimes is a ring. There is, you have to manage a large number of nodes in a broad geographical distribution, and the control channel is generally has limited bandwidth and are reliable. And so for all these consideration and for others, there are several issues for a network operator that has to manage a microwave network. Mainly, operator want to avoid to be in a single vendor hardware equipment, so to have a vendor lock-in. But obviously, this leads to interoperability problems. Network operation like configuration, maintenance, mainly are doing manual and not in a runtime. While on the other side, the more automation in operation would be desirable. The network management system are generally proprietary with closed interfaces. And so there is no integration between different vendor network manager and neither with network manager of other network domain. So SDN is seen like a feasible solution to all these issues, and that's why it is adopted in field in wireless transport, and its importance is going to grow further with 5G and beyond 5G. Next slide, please. So let's see in details which can be the advantages to introduce SDN in the management of a microwave network. So it allows a multi-vendor unified operation and maintenance functionality through open interfaces and vendor-independent resource abstraction. It allows a centralized control in terms of inventory, configuration, monitoring, performance data, and alarms. It always allows a dynamic adaptation to radio impairments, mainly by enabling automated frequency allocation, handling interference issues, and also implementing dynamic path protection and path redundancy. No, please, okay, thank you. It also allows dynamic adaptation to traffic changes requirement, so to be able to manage on-demand bandwidth assignment, managing traffic routing optimization and proactive rerouting, and also to manage efficiently power consumption in case traffic's demands goes down specific thresholds. And obviously all the items we saw before, together with the consideration that has been done, is a facility for the transport network slicing, mainly through radio resource abstraction in Northbound, and also allowing end-to-end QoS management that is the base in a microwave domain for the network slicing. The final consideration in introducing SDN in a 5G is that 5G aims to have a fully cloud-native architecture for all access, transport, and core network. And the SDN and network function virtualization are drivers for cloud digital transformation, virtualizing network resources, and enabling a software-based automation in network management. So next slide, please. This is a graphical representation of an SDN transport network that I think we already saw in slides before. Mainly, as you can notice, it follows a description that has already been shown. We can see all most significant elements of the architecture in an SDN microwave network. We can see the management interface between the domain controller and the network element. We refer to the southbound interface of the domain controller. It is reported the interface between the domain controller and the transport domain controller, that is the northbound interface of the domain controller. We can see the SDN application that are on top of the domain controller, both the transmission in domain controller and orchestrator, and the orchestrator itself that mainly is the focus to integrate different technologies as also access part, transport part, and data. Next slide, please. So what our activity in the standardization organization, referring to both northbound and southbound interface, is currently active. We are active in the ETSI, in the INDAS, the specification group for microwaves, mainly focused, as we said, in the wireless transport profile to define a common northbound from the microwave domain controller, but also studying a possible evolution in the southbound interface with the work item 25. And in the ONF, mainly for the specification of the microwave information model, the TR532 model, and where we also did several proof of concepts to demonstrate the availability of the model. Next slide, please. Here we have described a concrete scheme of SDN application that can be deployed on the northbound of a microwave domain controller, but I think that can be also extended to transport domain controller, not only microwave. We have organized this SDN application in main 4 different areas. We define mainly the control area, functionality that support operator to have and to maintain the full control of the network resources. So we talk about discovery, automatic discovery of the network, of the link, the service, inventory to be exposed in northbound, but also provisioning functionality to allocate and the resources available in the network domain. Optimization, functionality support operators in optimizing network resources. So to perform audit of the configuration and possible restoration, to perform operation for bandwidth optimization, and to application that performs analysis in the performance monitoring collected by the equipment and provided in northbound by the domain controller. Upgrade, functionality to easily upgrade the network in terms of hardware and firmware. So what we think to the zero-click service migration to install, to provision in new link, or the smart firmware upgrade to download the new firmware version in the network with simple operation and in few times. Automation, to implement network resources automation like the energy efficiency we described before, the traffic rerouting, and the preventive maintenance, so to be able to take action before some issues of congestion can happen in the microwave network. Okay, that's all from my part. So I leave the floor to the next contribution.
Thank you very much, Michele. Now it's time for Raul Boba from NC to talk about distributed ledger and smart contracts applied to networks.
Thank you, Carlos. Thank you, everybody, for joining the session today. My name is Rahul Boba. I am from NEC Laboratories in Europe. And today I'm going to talk about applying distributed ledger and smart contracts to transport networks. So many of you might be new to this topic, especially distributed ledger and smart contracts. So we will first go through an introduction, an overview of these two topics, and then go into the transport networks. So first topic is on the distributed ledgers and blockchains themselves. Realizing a distributed ledger of transactions. So what does it actually mean? So a distributed ledger is a special type of a database for ordering transactions. For example, in the case of cryptocurrencies, this could be ordering some notional value, or in other use cases, such as in the context of Terraflow, this could be the transactions could be some piece of information. What is unique about a blockchain or a distributed ledger is that it is append only, which means that nobody can modify or delete entries. You can only add to a particular database. Next slide. So if we have to break it down in terms of the core components of a blockchain, so we briefly discussed about that it is a distributed database at its core. So the innovation is not in how the new data is added, how it is maintained. And the data is always immutable because we cannot add a data, add any new form of data, and we cannot delete any new form of data. We can only append. We can always add data, but we cannot delete any data. A transaction typically consists of a transfer from a sender to a recipient. Within the blockchain scope space, there are two kinds of blockchains. So one are public blockchains. In the context of Terraflow, we will be using something called an enterprise blockchains, where the transactions are public, but only public to all the participating members. The transactions themselves, they are stored in blocks, and each block is a list of validated transactions. And each block is created independently by a set of blockchain nodes. Next slide. So what are the features of blockchain that make it interesting? So one is the replication part. So we are talking about a distributed database, and what do we mean by that is that the set of data that is stored by not just a single participant. In the case of blockchains, these are called a node, but it is distributed among the different nodes. So what this effectively means is that there is no single point of failure. So which is why you often hear the word that blockchains distribute trust, because you're not trusting a single source or a single entity. What this also achieves is kind of a decentralized or shared governance, wherein one party or one entity cannot unilaterally make changes. And because of this decentralization, you achieve a security despite Byzantine behavior. So Byzantine behavior describes an entity that is participating in the blockchain network that has some malicious intent. So in the case of permission blockchains, which we are using within Terraflow, we assume that more than 2/3 of the participants are honest. Or put it another way, as long as less than 1/3 of the participants are not dishonest, we can still achieve security of the blockchain. Next slide, please. So we briefly talked about blockchains. So I'm going to introduce another topic, which is also key piece of this technology, and that is smart contracts. So this will be slightly more technical, so bear with me. So a smart contract in itself is a self-executing piece of software that is installed on a blockchain, and the reason that it is that we call it decentralized is because it is not installed on any particular node or within any particular entity. So it is distributed on every node and entity. The smart contract itself is triggered when a particular transaction is sent to the blockchain. And what this achieves is that it achieves two things. So one is that you can automate business logic in a smart contract. So you can say that if you can take something like a simple piece of information that, if this party has received a shipment, then automatically compensate this party with a payment. So those kind of if-then statements can be automated on a blockchain without relying on a central party. And this is the key part of it. You do not need a trusted third party once you have smart contracts. So smart contract properties themselves, they are decentralized. They are always available. So as before, we were talking about the distributed ledger. So each node or each particular entity stores a copy of the smart contract, and they can execute that piece of software independently. They are also deterministic and transparent. So deterministic means that, you know, for a particular set of inputs, you can always expect the same output. And because of its distributed nature, they are also transparent. So any particular entity can independently review the smart contract and also simulate the output of a smart contract. Next slide, please. So I think so far we've talked about distributed ledger and smart contracts. Now let's talk about what we are doing within the context of Terraflow and how this applies to transport networks. So next slide, please. Oops. Can you go ahead? I think there is something missing. Yeah. Okay. Thank you. So let's look at the problems that are being addressed. So the problems that we are addressing is, one is the mainly the security aspect of it. So protecting the network and the infrastructure against external attacks. And secondly, we are increasing the trust in the network. So for instance, how can you be ascertained that a particular component or a particular device in a network is running the intended software? You can do, for instance, a remote attestation. So you can, without trusting a particular component, you can actually find out whether that component is running the intended piece of software or not. And then on the distributed ledger or blockchain, it's also used for obtaining reliable information and supply chain information. So understanding the origin of each particular component, what is the history of the software updates, all of that is reliably recorded on a blockchain. So how does a blockchain address these? So we discussed in the previous slide, so information is replicated across several nodes, and then it is synchronized using a consensus protocol. So we won't go into consensus protocol itself today, since that's a bit more complicated. Because of this replication and distributed nature, the blockchain is tamper detection and tamper resistant. So it is not enough that you change the information on a single node. You have to change the information on all the nodes on a blockchain. This also allows for transparency and traceability. So you can always have a reliable history of or record of the updates in a network, the topology of a network. It can all be reliably stored on a blockchain. And smart contracts themselves, so these can be as simple as an if then a logic, or it could be also be any complex arbitrary logic, and any kind of business logic or network logic can be automated within a smart contract. So using these features, what we are trying to achieve is that we are the goals are to enhance the device and network security and detect or resist tampering, and then allow for each blockchain entity or members to independently verify device status and details. Next slide. Thank you. So let's specifically talk about a few use cases that we've identified at this stage. So the first use case is a forensic analysis of resource allocation, forensic analysis. So what we are doing is we are recording on the blockchain in an immutable manner the device and component information. So what this allows us is to detect if there has been any malicious tampering, and also go to the extent of resisting any tampering. And with the feature of remote attestation, we can independently verify the history and details of a particular device or a component. The second use case that we have been looking into is the wholesale of transport resources. So given that the information in the blockchain is distributed across different nodes, so it is very well suited for transportation of information. So in the case of the wholesale market, so there are local carriers and wireless carriers that would like to rent resources from larger carriers. And in this case, what we actually need is a timely configuration to meet the different traffic requirements. So we achieve this by supporting multi-tenancy using the blockchain, where the information is recorded and transported across the blockchain to different components, and thus we can meet the requirements of transparent and then transparency and non-interference and security. Next slide. So this is kind of the final slide that gives an overview or brings together the different pieces. So the previous speakers have talked about the architecture of the Terraflow OS, and you can see here where the distributed ledger is located, and how we plan to achieve these objectives is through recording different information on the blockchain. So this could be runtime information, this could be component information, this could be information around the history. We record the information around the software status, and get remotely attest the software integrity of any particular component or a device. And every component, every component within the Terraflow OS will have an ability to use an SDK or an API to communicate with the blockchain. And we will be using the smart contracts for a number of purposes. So the basic would be to read and write information on the blockchain, and then more advanced use case of the smart contracts would be to look at the device and topology information and then provide some security assessment. So with that, I have finished this part. I give the floor back to Carlos, and happy to take any questions that the audience may have.
Let's keep the questions for later. So now we will have the latest for today on our transfer SDM standardization efforts for the team, for all that consulting. But remember that at the very end we have a Q&A with the experts, so please start working with questions and slow the floor to you. Thank you very much.
Hi, good afternoon, everyone. It's Dan here. So I'll be talking about some of the standardization efforts that a number of the earlier presenters alluded to. Next slide, please. So I guess, first of all, why standardize? It's obviously a way to demonstrate technical leadership whilst sort of facilitating development of key technologies, in our case relating to the internet, the services and applications that are running on top, as well as some of the application and sort of IP layering. Standardization is really important for sort of facilitating rapid deployment of new technologies in order to ensure interoperability, especially and help with sort of innovation development. And of course, through the approach, depending on which standards organization you're using, you're essentially working through a community of like-minded individuals. You're working on a consensus approach. So you've potentially got access to a wider pool of engineers and experts to help with developing these technologies. Within Terraflow, we've seen sort of the overall objectives outlined very early on by Ricard, and then some of the architecture by Juan, and then some of the business cases, the commercial objectives of Terraflow are extremely important. So when we're developing new technical solutions and technologies, or maybe helping polish existing proposals, these technologies are underpinned by commercial requirements, and I think that's something that Terraflow's done really well very early on in the project. We know that in the past, with some of the European funded projects, there's been an emphasis on maybe blue sky, greenfield research and networking, and not so much emphasis on the sort of the commercial applicability. And I think that's really where Terraflow is doing things slightly differently. We've got some great technology that we'll see shortly, but we're also looking at those commercial drivers as well. So the standards can be sort of split into two broad categories. The first is sort of formal standardization. This is where we see organizations like the ITU, maybe ETSI, maybe IEEE, TMF, etc. These are organizations that have been around for decades. They can be extremely formal. Often participants are at sort of government levels, or senior members of sort of technical organizations. And then we've got the sort of the increasingly, the rapidly expanding informal standards, and let's call them specification organizations as well. So this is where things like the Linux Foundation project, essentially creating an ecosystem for open source projects that can interact and relate to each other regarding sort of systems and services around data centers, and also now the internet. They demonstrate that standards can be developed by sort of developing code and publishing that code, and using that code as essentially a well-defined specification or standard that then gets used at scale and by a significant number of implementers, and it becomes a de facto standard. So for Terraflow, it's very important to engage in both these types of categories. So we can see on the slide here that there are liaisons and sort of active participants on the use case development, some of the sort of high level architecture, and then some of the key components. We saw just on the previous presentation, the distributed ledger, and essentially there's an open source project called Hyperledger there. We've got the automation requirements of Terraflow. So these are maybe some conceptual, but those will ultimately lead into sort of process, procedural, and then things like resource models for managing automation in the network. Because unless we can have sort of high level intent, and I think Juan mentioned Northbound Interfaces, to sort of low level device or specific resource models, which we might call sort of network policy. Without those models and a method to map them, simply automation is not going to be possible. And then sort of another area of standardization that Terraflow is working on are those device models and the policy models and some of the service models that were mentioned, I think, during the Volta presentation, the L2 SM and L3 NM. So it's very important, I think, for the project to work across all of these different categories and classes of specification and standards organizations, but also through our sort of architecture, and this is sort of done in WP3 and use cases, sort of be able to link all of these different standards together. Next slide, please. So this is just a current snapshot of key specifications and standards that the Terraflow team are currently working on. It's not completely exhaustive. You know, we're adding to this list almost monthly at the moment as well, but it gives you a good idea at that sort of that strata I just mentioned, which is sort of high level requirements, use case, in some cases maybe a problem statement, and then some of the other standards work right at the device level, and sort of from a southbound interface perspective, we might be talking to IP devices or MPLS devices or optical devices, or we might need to sort of take a concept like a network slice and map that into a series of resource models. So there's a number of sort of really important specifications and standards here. And regarding this list, Terraflow essentially is either the lead author or a major contributor to every one of these specifications and standards that are mentioned on the slide. And another area, an important area of specification and standardization is the operational aspect and security. And we saw earlier that cybersecurity is an important dimension within Terraflow. So that there needs to be sort of coordination between the different stakeholders for identifying security risks and being able to kind of negate or mitigate some of those issues. And in some cases, it will be around sort of best practice for hardening some of the core functions, for identifying maybe the external interfaces between some of the functional components, and considering what are best practices for things like REST APIs, and where there are, you know, potentially security issues, potential holes. You know, those threat vectors need to be identified, and then we can go back to those sort of standards organizations and say, look, there's a potential risk here. We need to either use a different protocol, or we need to kind of harden or patch the existing mechanism. One area that I would like to kind of highlight on this slide as well is policy, and especially that intent to policy mapping, which is conceptually very easy to explain. You know, what you want in terms of the intent, how to deliver it, that is the policy. But for a sort of a computer system, especially a sort of a complex distributed system such as the Terraflow operating system, we know that there is a multidimensional approach to this intent to policy mapping, because the resource is both network, it's application, and it's also sort of compute and storage and potentially function as well. So I think this will be a really exciting and important area of standardization. Next slide, please. So finally, this is just sort of a high-level view of some of the architecture of Terraflow. This is sort of almost at a maximum sort of zoom, sort of at a very high level. As soon as you take any one of those individual blocks and increase the magnification, then a whole series of functional components and potential interfaces will appear. But at this sort of high level, you can see where I mentioned earlier, sort of the use case discussion, commercial requirements, applicability, and problem statements. Well, the ITU, things like FG Network 2030, and also the more recent FGAN, the Autonomous Networking Initiative. Those are great opportunities for Terraflow to collect consensus and thought from leading researchers outside of our project, and also in some cases outside of the European Union, and help use some of that discussion to sort of drive internal development and discussion, but also when we look for solutions or we're working on protocol solutions, then that's just additional sort of data or evidence, empirical evidence to justify why some of the design decisions are made. The sort of dropping down the Terraflow stack here, we start moving into the application layer, and where some of those software components that were highlighted earlier around the contract management, the distributed ledger, and some of the SDN controller, the higher layer SDN controller work, and very important, the orchestrator function, the thing that will cooperate between a series of lower layer software functions. There is a number or several open source software components that are going to be key. And again, that kind of leads us to that sort of informal path of specification and standardization by participating at things like Hyperledger or open source Mano or Honors. We're directly contributing code and helping sort of shape that sort of future specification or standard. As we start moving towards the network layer, some of the important work around service modeling, network slicing, device and resource management becomes critical. So these will be things like Yang models, maybe some internal models that we use for resource management, sort of proto buffer, and then sort of ongoing use, and maybe some sort of findings when we start using things like gRPC or netconf to actually carry this information and encode our requirements between functional components or from a network controller or some kind of maybe provisioning device to the physical or virtual device itself. There'll be opportunity for us, as in Terraflow, to sort of contribute within relevant working groups within an open source community, or say the IETF, or things like netconf and RESTconf and PSIP, etc. So you can see on the overview here a number of sort of dotted lines. Essentially these are external interfaces where we would need to have a well-defined protocol and procedure for things like error handling and resource management, and then the logos of the relevant standards and specification organization, and most of these organizations that are highlighted on the slide have actually been mentioned in some of the earlier presentations. So this quite nicely, I think, sort of shows how they kind of fit into the overall architecture. So I think that's really the last of my slides. This was a sort of a 10-minute presentation with a 2-minute Q&A. I know that we are now running under time, so there is the opportunity for questions. So if someone would like to ask a question, that would be very well received.
Well, Daniel, we already have one question. It states that Terraflow appears to be making contributions to such a large number of SDOs and using output from even a longer list. How do you think Terraflow can coordinate across SDOs, and how does the project handle this competition that we are observing between SDOs?
Oh, that's a great question, and I've kind of started to smile at the word competition, and I think it's a really good observation. Clearly, there is overlap with some of these organizations. Looking at the diagram on the final slide here, there are a number of Yang models, for instance, in OpenConfig that you have an IETF equivalent. And there are sort of device models, service models that are defined in the ONF that also have an IETF equivalent. So there is clearly, in some cases, either overlap or direct competition. I think for Terraflow, we've kind of taken a perspective that we want the best in class, and the particular model that's most suitable for our implementation and our deployment. In an ideal world, there wouldn't be this kind of overlap, and we, a number of us involved within Terraflow are also sort of technical and administrative leaders within some of these organizations, and we absolutely try to minimize that overlap, both sort of personally, because it creates more work and it becomes almost a denial of service attack on people's times, because there's only a limited number of people that can engage in these organizations. And it's something that really sort of started happening about 4 or 5 years ago, and there is no easy solution right now, because there's also a lot of financial investments typically from vendors and some operators within these organizations, and no one wants to kind of cut off either potential funding or development of a particular technique or a proposal, even if something in another organization is actually better. So there's no easy answer, I'm afraid, except that we should all, as a community, try to minimize the overlap and focus on the technical aspects rather than some of the more commercial aspects.
Thanks a lot, Daniel. Now we have one question from Juan Pedro, because he has been presenting the different Terraflow scenarios. But I would like if we could follow up a little bit and explaining how does Terraflow is coordinated with the internal efforts of Telefonica for migrating and transforming their whole network.
Now without a mute. Okay. Yes. I think that's the work or the work that is being done in Terraflow is totally aligned with the migration or process in Telefonica to implement an SDN architecture. And I have to say, not only in Telefonica, because we are currently coordinating with other operators within the Telecom Infra project. We created a new group that is called MAST in this in TIP, in the Telecom Infra project, because all of us think, like Telefonica, are really looking for a vendor agnostic SDN architecture. We are facing the same problems, that is the introduction of an SDN architecture is being delayed because of a lack of a standard or lack of specific standards for both the southbound interfaces from the controllers to the devices and the northbound interfaces from the controllers towards the applications. So in Telefonica, we are also working on this. Terraflow is targeting, let's say, more innovative or future use cases. But currently, for example, in Telefonica, we are working with the use cases that are needed for the day by day. For layer 3, for example, layer 3 or layer 2 VPN, provisioning, topology and service inventory, or performance fault management. All the use cases that are needed nowadays are being currently in Telefonica and also with other operators. We are working on the technical specification in order to do all the data modeling, for example, in the IP network, for NetConf and on the open config models in order to support these use cases. Also the northbound interface to expose this information towards the applications. And we are following this the same methodology that we are applying in Terraflow, we are currently applying in Telefonica for the short term. First of all, identify the use cases working with the planning, the engineering, the OSS teams, and so on. Once we define the use cases, we provide a technical specification based on mature standards. If we identify a gap in the standards, then we we provide the required contributions, also in alignment with other operators. Third one, we have the technical specifications, because these are being requested in the RFQs, in every purchase process in Telefónica, in the IP, in the optical, or in the microwave. We are including as a mandatory requirement the support of these interfaces in both sides, the network elements and the SDN controllers. And third, of course, we need to do a testing and validation of the solution provided by the suppliers. And then we have a gradual activation of these use cases in the field in order to enable also the integration of the OSS, of the operating and supporting systems, with the network, always using these standard interfaces. So the process, the same methodology that we are proposing, and we are working in Terraflow for, let's say, future use cases based on machine learning, artificial intelligence, or the management of Terraflow connections. The same methodology and even the same architecture is currently being applied in Telefónica. I encourage all of you, if you have time, to take a look on the Telecom Infra Project website in the OOPT group, Open Optical and Packet Transport. In this OOPT, you can find the information, a white paper about describing the methodology for in this MAST group, what is the SDN architecture, the use case methodology, and you can also find the first deliverables that were published in this group, specifying also both the northbound and the southbound interfaces in IP and optical for a given number of use cases, mainly targeting service provisioning, topology, and inventory. So in Terraflow is an extension of looking at the future of the work that is currently being done in Telefónica and in other operators looking for an standard SDN.
Well, thank you very much, Juan. It was very helpful to align. I think that the operators needs with the solution that we are proposing. And now we have a question for Dr. Boba from NEC. The question states that the security of containerized applications has been an increasing concern. You mentioned that this tutor lecture can be used to validate software. Could it be used, this tutor lecture, to validate the state, the version, the code running on a container? I don't know, Rahul, if you are available and you can switch your camera. If not, I will try to answer by myself, but it's better if you can provide. Okay, looks like Rahul is not available, so let me try to answer it. My answer the first one would be yes. It's true that this lecture can be used for this kind of activity, so it could provide this tracing of the different software and mechanisms that are being used by using containerized application. But let's remind that we are on the different applications that we are running from the operator's perspective. They are in the closed environment of the operator, so that these are not applications that are being deployed by the different services, not yet. So we are providing these cloud-native applications for the SDN controller. It's true that they could be traced using the distributed technologies, but the environment is secure enough to apply other techniques. We see the deployment of the lecture, whether we have untrusted scenarios. So that's my answer to the question. So we don't have any other question. I don't know if there is any burning one. Please write them on the Q&A or write them into the chat. If not, we will conclude the session. Let me, I don't see any questions, so let me thank all the speakers again for their contributions. Let me thank all attendees for your interest to this workshop. I hope that you subscribe to the different Terraflow media channels and we keep in touch. Okay? Thank you very much.